Hi, my name is Jim, and today we're going to be talking about the basic elements in AC circuits. And the elements include capacitors and inductors and, of course, resistors. And just for a reminder, impedance, symbol Z, is the opposition to current flow in an AC circuit, and that may involve an R, an L, or a C, or any combination therein. So first off, the unit of the capacitors is the farad. It's capital F. For most applications, that's quite a large amount. And capacitors store electrical energy in an electrical field, and this is potential energy, meaning that you can charge up a capacitor, and if it doesn't leak, meaning it's a good quality capacitor, like an oil-based capacitor with an insulator, you can walk around for a couple days and get a shock from it. And the energy stored in a capacitor, W equals 1/2 CV squared, and the unit is joule, joule like in ring. And notice that it varies as you square the voltage, so there's a significant dependence upon the voltage. And a joule is a watt second, not a watt per second. It's energy, kind of like kilowatt hour on your electric meter. So conventional current convention here is that if we have a capacitor plus minus as current flows through it with a designator C above it. So the fundamental equation of a capacitor is IC equals C, that would be the value of it in farads or microfarads or whatever, times dV dt. And what dV dt is, it's math speak for rate of change, which I'll refer to as ROC. So the faster the voltage changes, the higher the capacitor current is. So if we expand this a little bit, and what we're going to do is have the V here, which is the voltage of the waveform, be equal to a sine wave. So IC equals C times ddt. So this is a differential operator, and the voltage function is V peak sine of 2 pi ft, kind of like what we've seen before. Now, you probably don't know how to manipulate this, but what happens is that when we talk about rate of change, if I start out with a black sine wave here, what I see is if I increase the amplitude, the rate of change in the negative going direction is steeper for the larger amplitude signal, meaning that if I drew a tangent here, it would have a more negative slope than that of the reference signal in black. So what we can say is that the rate of change is greater for a larger amplitude signal. Likewise, if the black sine wave is our reference and I say double the frequency, I think you can see that the rate of change here, that would be the slope in the negative going direction, is less than a rate of change here. So rate of change is also a function of frequency. So what we end up doing is pulling these terms out, so the capacitor current would be equal to C as before, and because it's related to the amplitude of the voltage, we have a V peak term here, and because it's related to the frequency of the voltage, we have a 2 pi f here, and the rate of change is related to the cosine function of 2 pi ft. And remember, the cosine is just a sine wave that is shifted by 90 degrees. So we have a term in here that relates to the amplitude and to the frequency, and also, of course, to the value of C that determine the capacitor current. So as before, a capacitor current is a cosine function, and this will be our schematic diagram, which in simulation software would not work. We would have to have a very, very small limiting R there. I won't go into that now. But what we can see here is that if the black signal here is the voltage, and it would be good to look at the green signal, and this is normalized to 1, so I don't get all those terms in there and have large and small values on the same graph, is we can see that this is the cosine function that's leading. Now, it's maybe best not to think of this as a waveform, but as a collection of data points. And what's important to note here is that when the sine wave goes through 0, the cosine is 1, which means the rate of change at this point is the fastest in the positive going direction. Likewise, at the very top of the sine wave, and if I were to draw a tangent line, I'd end up with m, the slope, is equal to 0 for that very, very instant, an infinitely narrow instant in time. And the cosine wave tells us that, well, the rate of change is 0. Exactly right. Now, when the sine wave goes through 0 again in the negative going direction, the cosine is -1, indicating that this is going to be the maximum rate of change in a negative going direction. And then when we get down to the 270-degree point, again, what we could do is draw a tangential line and see that m would be equal to 0. The cosine function is 0, telling us that the rate of change of the sine wave right there is 0. So look at the cosine as kind of like a set of data points that tells you the instantaneous rate of change of a sine wave. Now we're going to be going somewhere with this. This is good background information. We're going to build on it. But in conclusion, when I leads V, I leads V by 90 degrees. Okay? When I leads V, the circuit is capacitive. So it doesn't matter if the circuit has a capacitor in it or not, true or false, but or true rather. That's the definition of a capacitive circuit, is that the current leads the voltage. A pure capacitor, as in doesn't exist, I leads V by 90 degrees. So the opposition to current flow that's produced by a capacitor, and this comes through the mathematical work of a scientist called Euler, spelled with an E, is called reactance X, and the subcomponent is either going to be C or L. So in this case it's X sub C, capacitive reactance, is equal to the quantity 2 pi Fc raised to the -1 power, that is most usually expressed as 1 divided by 2 pi Fc. And what you need to be very careful of if you do this on a calculator is that when you go to do the division, is that you parenthesize that, or you're going to end up with 1/2 times, by the rules of precedence, pi Fc. So also calculators have a -1 button on it. And if you just enter 2 pi Fc and hit the -1 button raised to the -1 power, the law of exponents will give you this form and solve your answer. So when I say the word capacitive reactance, and remembering that we have phasors and so forth, imaginary components, it implies -J. It's built into the word. Just like signal loss equals a gain in -dB, is built into the word loss. Ripple rejection ratio has a negative built into it. It automatically infers a loss. So for example, if we take a simple circuit here, and we'll let C be 100 nanofarads, that would be 10 raised to the -9th. We'll let the frequency be 1K, and the voltage in the circuit here be 10 volts peak. First order of business is to determine the capacitive reactance. So that would be 1 divided by 2 pi Fc, and there you see I've elected to write the 1001 kilohertz as 1000 because I can hit the 0 buttons pretty quick. And for the value of the nanofarad, for the 100 nanofarad capacitor, it's 100 e to the -9th. So you have to be comfortable with entering values in engineering notation, highly preferred over scientific notation. It will save you from making mistakes. So here's our circuit here. Then it's just a question of voltage law, Ohm's law. So capacitive reactance for these values comes out to be 1.592 kiloohms, and the current flow equals V over X sub C, and that comes out to be 6.28 milliamperes. Okay, we know the magnitude, but, well, what about the angle? So we have to kind of take a look at that next. And usually this is done all at the same time. I'm just breaking it out for demonstration purposes. Now this may be a bit confusing because we have circuit diagrams, and there's current diagrams, impedance diagrams, voltage diagrams, and coming forward in a little while there's admittance diagrams, and the direction of the reactance or the current or the voltage many times is different depending upon the diagram you're using. So in a current diagram is what we know is that the current leads the voltage, so we would express that as a phasor in the plus J axis, and that would be leading, and the value would be J 6.28 milliamperes. Okay, in rectangular form, if we wanted to discuss what that value would be, that current would be 0. There's no real component here. Plus J 6.28 milliamperes. In polar form, capacitor current would be 6.28 milliamperes plus 90 degrees, which would be the angle in here. So depending upon what we're doing, we may want it in rectangular form or in polar form to ease whatever math that we have to do to solve a circuit problem. Now if we look at the impedance diagram, the impedance of a capacitor is negative J. Here's our 1592 ohms, and I put a dot there on the negative J axis. So in rectangular form, if we wanted to express the impedance, it would be 0 minus J 1592. 0 because there's no real component here. There's no resistance in the circuit that we had up on the other page with just a generator and a capacitor. In polar form, we would have ZC equals, and what the impedance of a capacitor means, I should say this, is that it includes any real part. If it would be there, it's the whole opposition to current flow. Now for a pure C, again, the real part is 0, so in polar form we would have the magnitude in ohms of 1592, and the angle would be negative 90 degrees, which would be this guy right here. So which form do you want to use? Depends upon your calculation. Finally, let's take a look at the frequency response of the capacitive reactance. So F is going to be the abscissa, and the capacitive reactance is the ordinate. And if we were to plot this guy out, as what we would see is we would have two asymptotes. Now, what an asymptote means, and this would be a horizontal asymptote, is approaches but never touches. And a vertical asymptote in the same way, and this here would be 0 frequency right there, means that the capacitive reactance approaches infinity but never quite gets to it. So to do the math and to make it realistic, I suppose, is what we use is a mathematical term called a limit. Now we know where this is going, and we know where this is going, but a limit is just math speak for defining it. So if we take the limit as f goes to 0 of 1 divided by 2 pi fc equals infinity. So if f could get to 0, it would be infinity. Likewise, if we take the limit as the frequency goes to infinity, meaning this way, the limit of 1 over 2 pi fc would be equal to 0. So if we could make f infinity, the capacitive reactance would be 0. So that's the trend of it. And when we talk about this, here is actually applied. So the limits are put into place, per se, by the way they plot on the current diagram and also on the impedance diagram. Now, what does a real capacitor look like? Not so good. A real capacitor has the capacitor, of course, and in series with it is a small L, small inductance, which is called ESL, effective series inductance. It's there. It causes this, instead of being a pure asymptote, to rise in frequency, because we'll see what the equation for this is, which is proportional to frequency. That's the inductive reactance. And we also have a component called ESR. That's effective series resistance. So if your replacing a capacitor in a switch mode power supply, like in a TV set, a computer power supply, or whatever, you have to use a capacitor with a low ESR, or the switch mode circuit will eat the capacitor. They cost more, and in some cases manufacturers of the ICs that build the switchers will tell you manufacturers and part numbers to use. It's that critical. Now we got this nasty little guy off to the side here, which is called the dielectric constant. And there's a phenomenon in a capacitor where some of them are more prone to this, as electrons bury themselves in the insulator. So we have two conductors separated by an insulator. So U is a bag of salt water as a conductor, air is an insulator, and the nearest metal thing to you, well, there's capacity between the two of you. It's not physical, but it's still there, and probably a very low value. So in dielectric constant, what happens is that some of the electrons, when we go to discharge the capacitor, get stuck in the dielectric. And we could leave a short circuit across the capacitor for, I don't know, a minute, come back an hour later, and then measure the voltage, and it might be, say, half a volt. So it's a nasty phenomenon, and usually very much not desired. I first learned of it when I was repairing a 21-inch black and white television set, and there's a connection for the high voltage on the side, which is about maybe 20,000 volts. So I discharged it correctly, and my parents didn't have a dryer, and they hung the sheets on a clothesline in the basement. So I'm carrying a 21-inch picture tube at 14.7 pounds per square inch pressure and a near perfect vacuum on the inside, and my arm comes in contact with a damp sheet along with the terminal on the picture tube. So I'm juggling a 21-inch picture tube, and it doesn't explode, it implodes, and then all the pieces hit each other and fly apart. Thick glass, very dangerous. I wanted the neck on one, and I carefully hit it with a hammer, and the explosion was relatively large. Implosion, explosion. So kind of upset my father a bit. Anyway, gotta watch dielectric constants. Our next basic element is the inductor L, passive current convention, plus the minus current flowing in this direction. Here's L. The unit is the Henry, capital H. And an inductor stores energy in a magnetic field, and this is kinetic energy, whereas a capacitor stores potential energy. So basically, the current flow produces a magnetic field, and when you interrupt the current flow, the magnetic field collapses. And thank goodness, or our spark plugs in our cars wouldn't work. So that's the function by which we get sparks and other high voltage kicks that are sometimes useful and sometimes very destructive. So the energy stored in an inductor is the energy equals 1/2 L, the inductance, times I squared, and again the unit is joule, where that equals 1 watt-second. So the fundamental equation for an inductor is VL equals L di dt, where di dt is the rate of change of current flow. So we're going to take that and expand it into sine waves. So the inductor voltage equals L, and this is the mathematical operator that requests the rate of change, ddt, and the voltage is defined as I peak sine of 2 pi ft. So as before, when we take the derivative of this, finding the rate of change, we end up with the inductor voltage equals L, which we would inspect, is proportional to IP, as was the capacitor proportional to Vc, is also proportional to the frequency. So we end up with these terms sitting as a multiplier to the cosine function. Just as before, I'm not going to draw it, but so we have the cosine there, and remember that the cosine is a sine wave with a 90-degree angle, 90-degree shift. So what we would have if we wanted to plot this circuit is we would have V, and the current would lag by 90 degrees. So what we would really say about this, the way I've defined it before, is that the voltage leads the current by 90 degrees. And we could also say that in the opposite way, as the current lags the voltage by 90 degrees. Now, what you should note here is this is exactly opposite to that of a capacitor. Okay, so these are kind of diametrically opposed parts. Potential energy, kinetic energy, lead 90 degrees, lag 90 degrees. So, in conclusion, any circuit where I lags V is considered to be inductive. In a pure inductor, as in no such thing, I lags by exactly 90 degrees. Now, Euler defined the formula for sine waves only, and you need to know this. On the opposition to current flow, again, is X, reactance sub L. X sub L is inductive reactance, and it's equal to 2 pi FL. Learn this. You're going to be using it like forever. So for an example here, if we let F equal 1K, L equals 500 millihenries, and the applied voltage is 10 volts peak, and we're assuming zero angle here, didn't write that down. To find the magnitude of X sub L, it's simply 2 pi times 1000 times 500 e to the negative 3, or I could enter this as 0.5. I like to get this in front of students so they get used to seeing that inner exponent. And in this case, the inductive reactance comes out to be 3.14 kiloohms. So what's the current flowing in the circuit? And I would be equal to V over X, as before. 10 volts divided by 3.14 kiloohms comes out to be 3.10 milliamperes. And again, kind of forgot the angle part of this. I didn't forget it, but I didn't include it. But you can see here that Ohm's law applies, and instead of R, all we have is X in the denominator, the opposition to current flow. So, putting it together here for a current diagram, in rectangular form, the inductor current would equal in rectangular form, the inductor current would be equal to 0, meaning there's no real current here, minus J 3.10 milliamperes. So it'll be sitting on the negative J axis. It's a phasor, so we have a little dot there, exactly on the J axis. In polar form, since we don't have a real component, the current would be 3.10 milliamperes again, but the angle would be negative 90 degrees. That was good. Let me fix that right now. Negative 90 degrees. Okay, once again, IL, because there's no real current flowing, would be equal to 3.10, which is the magnitude in milliamperes, shifted toward the negative J axis at minus a negative 90 degrees. Now for the impedance diagram, in rectangular form, since there's no R in the circuit, it would be 0 plus J 3.14K. So I put a dot up there on the plus J axis. In polar form, well, again, there's no resistance in the circuit, so we would have the impedance Z sub L equals 3.14, and that's kiloohms, at plus 90 degrees. And 90 degrees sits right in there. 90 degrees sits right in there. Okay, so basically what we have is a bunch of dangling participles with L and C. And when we start to put them together in circuits, we'll apply this stuff and it'll start to fit together. But this is just an introduction to what the basics are. So let's look at the frequency response of an inductor with respect to frequency. And what we see is that X sub L is directly proportional to frequency. And we might expect that because we do not have any reciprocal relationship like we did in the capacitors, which led us into an asymptote, which led us into the units of, or using limits. So a real inductor is anything but a coil of wire, of course. It's always complications. And what we have is, and this is the coil here, is a series R, and that kind of makes sense because it's made out of wire, and wire has resistance. And there's distributed capacity between the windings, which I tried to show by these C's that are embedded in the coil. So these aren't physical parts. It's just that one part of the coil, another part of the coil is wire, and between two conductors there's an insulator, and the C gets distributed across the whole thing. So an inductor basically has a point of self-resonance, meaning that at some point the magnitude of X sub C equals the magnitude of L, and we'll save that discussion for another day. So in summary, the whole thing is if the black signal equals the forcing function, the voltage, and we take a look at the capacitor current in blue, we see that it is leading the voltage by 90 degrees. And if we take a look at the inductor current in green, we see that it is lagging the voltage by 90 degrees. Now this is going to lead to some very, very useful circuit phenomenon a little bit later, which allows us, say, to turn on a radio and listen to a station. So that's it for the basic components, and there's a lot here, and the current diagram with the phasor going one way and the impedance diagram with the impedance represented in the other way is confusing, but it's necessary to learn this, and over the period of weeks you'll be becoming very used to seeing it. So that concludes the discussion on basic elements, and stay tuned. We'll be putting these to use in series circuit, which you caught a glimpse of last time, and thanks for watching.